How about this? What haven't I used? How we picked h. So we'll pick h now. Well, we know this is just less than this horrible thing. X minus t to the n over that thing. T. Oh, sorry, I made one mistake. Wow, I forgot about this. Let's pick h to be less than this and h to be less than 1. Let's do that. It'll save me in a second. So this h is less than, you can do that, right? You can say make it less than this and whichever one's smaller, make it less than that one. And I realized why I want that because I picked this to be t plus 1 to the n, or minus 1. So the point is, well, this isn't so bad because again, just by what we said before, this h is less than 1 because I just added that. This also, oh gosh. I mean, I've sat in so many analysis classes, and you don't understand how many times, like somebody will be doing the proof, goes back and changes some assumption previously to make it work later. Because I realized, oh wait, I did these numbers, I must have been assuming it was less than 1. But anyways, we know this is also just less than x minus t to the n, t plus 1 to the n minus 1 times t plus 1 to the n minus 1, which is just equal to x minus t to the n. Yeah?
How would we put all those conditions together? How do we know that h is less than something, right?
Yeah. What, x is less than something? H is, yeah, we're choosing h to be less than two things. How do we pick it? Well, one of these is a smaller number, right? The point is if t is extremely small, like 0, this could be a very large number. Like very close to 0, this could be a large number. But I also am assuming it's less than 1. I'm just saying there's two numbers, so if you wanted to be precise, you really should say pick h to be less than the minimum between these two numbers. Does that make sense? And one of them is smaller, so it's less than that is less than both. But okay, I'm not going to write that, but that's what I really mean. Does that make sense? So I'm here, why am I done? Add t to the end of both sides, or just do what we already have like a theorem that says this. So this implies t plus h to the n is less than x, and we're done. Yeah?
So now you have less than or above, you have less than.
Yeah, I got the less than here. I got the less than strictly here. Right, but this is a chain of inequalities. As long as you have less than or equals, you can carry over the equal. As soon as you have a strict less than, you have to switch over. Make sense? And I got that from my choice of age. It really did make it, in fact, to be frank, the way I stated lemma 3, it's actually probably strictly less than. When I worked it out in my head, it was less than or equal to. And I'll tell you another secret, in 90% of analysis proofs, that equal sign doesn't usually matter. Or probably more like 95, 97%. The only time you care about, right now we do care about the equal sign, right? We don't want that to be x. We want it to be strictly less than x. But you can just pick h to be small enough that it doesn't matter. But there, I proved it. But and again, yes, this seems like a mess, but the idea is the important part. I take a t and I need to find some small enough thing that when I add it to t, it's still to the nth power small. That's the idea. That's all I needed to do. And then, of course, a lot of clever inequality stuff. Trust me, that comes with experience. At one point, like these inequalities were as mystifying to me as they probably are. Like when I first saw them, I always thought these were crazy. But now, like I've done these for years and years, I see a lot of these inequalities automatically. But great, and if you guys really want to know what's the difference when I'm doing it for the parentheses version, I pick an h that's a slightly different h and I subtract it from t. Then I show t to the n minus that t minus h to the n is small, just like this. And you do the process is exactly the same. If I remember correctly, what you're looking for in the other case is something like t to the n minus x over n times t to the n minus 1, maybe something like this. And if you subtract this from t, and t is bigger than, t to the n is bigger than x, this will still be bigger than x. All right? Other questions about this proof? Tougher. I know it's tougher. But actually, if you look at his proof in the book of the theorem, this is actually 2/3 of his proof in the book of the theorem. So now instead of going through the whole proof of the theorem, let's just lay out exactly how the whole story is going to go. So I'm going to do proof of theorem. I'm not going to erase the lemma. I just erased the lemma. That's great. There exists, what did I say, s in R, s greater than 0, s greater than t such that s greater than t such that s to the n is less than x, s to the n is greater than x. Okay, fine. So now we're going to prove the theorem. And now we have all the things we're going to use up here. So, but let's just think about what we're gonna do. So I know you guys are still getting used to all the new words we're starting to use, but let's pretend you wanted to find the nth root. I'll give you a hint. Using supremums, what kind of set do we want to start with? Or, like, we're going to use the supremum to find it. So what set should we look at? What's that? Right. So let's consider this set. Like, if you're thinking about it, well, okay, I'm going to try to use the supremum because Ivan's telling me so. So what has as its supremum? The nth root of x. Well, if anything does, if there's justice in the way, this set should. So all, let's say t and r, let's say even t positive, just to make things easy, such that t to the n is less than x. So the first thing is we consider this set. So this is going to be more of an outline than it is the details. But I'm just going to tell you how roughly it's going to go. So now what do I want to do? It's show it's bounded above. That'd be good. Sure. Right, so we actually have to show two things. So we want to show first it's bounded above. What else? So maybe I'll even say want to show. E bounded above, and what other thing do we want to show? Not just, you need one more thing. To have a supremum, what else do you need? You need to be bounded above and? But something else? Not empty.
The piece something property?
Right, we have that already in R. We have that for free. What I'm saying is what we're missing is that E can't be empty. So we need to find something that actually is in there, and we need to find an upper bound for this thing. I don't even remember what I chose for the upper bound when I did this proof. I've already lost the page. Oh yeah, sure, that makes sense. So let's just do bounded above. So let's say E is bounded. How are we going to show E is bounded above? Well, the idea is just that if you take t to be bigger than 1 plus x, you can show. So this is an outline. This is not the proof. You can show. So Rudin shows t to the n is bigger than x. So 1 plus x is an upper bound. What he does is he shows that anything bigger than anything bigger than 1 plus x is not an E. So that means 1 plus x is an upper bound. Okay? So that's bounded above, and then the next thing he does is he says he gives you this guy, x plus 1 minus or x plus 1 over x. Well, it turns out you can show pretty easily this is less than x. If you want me to show that, I will, as long as x is positive. So you show this, and the thing is, what else can you tell me about this number? Like, for instance, 5 divided by 6, 4 divided by 5, 3 divided by 4. No. What? What's that? They're always less than 1. No matter what x you put in there, this denominator is bigger than that. So this is also less than 1. And it's less than x. So this to the n is less than this, which is less than x. So this, by lemma 2, this to the n is less than x, or is less than itself, which is less than x. Does that make sense? Because this is less than 1. So when you raise it to a power, you get a smaller number. So you get that this is x. Or this is less than x, which is what we want. So it's not empty. So these are the two steps he does. So then he says, oh, it has a supremum. So we let alpha be the supremum. So if we let, so now E has a supremum. So let alpha be the supremum of E.